Yeah, good afternoon, everyone. I'm Sanjiv Satoor. I work in the developer tools team, mostly on the CUDA profiling products. Here, we are going to try and give a quick overview of the NSIGHT products. And yeah, uh, each one getting into details can be a different presentation, but we're just trying to, just like what was done for the HP tools, we'll try and give an overview of what tools are available for GPU development and debugging and profiling. Next slide, please. Yeah, so broadly, the tools can be classified under CUDA tools and graphics tools. Under CUDA tools, we also have optics tools, which is a library for which supports ray tracing. So here, the different tools available are shown in classified. So for code development, we have build management, editing, debugging, and core dump tools. These are integrated as part of the Visual Studio and Eclipse IDEs. We also have standalone tools broadly in different categories. We will talk in some more detail on NSIGHT systems, which is for system trace, and NSIGHT compute, which is for CUDA kernel profiling. For deep learning, we have recently launched a new tool called NSIGHT Deep Learning Designer, which allows you for DNN code generation and design of the DNNs. On the graphics side, we have NSIGHT Graphics, which supports API debugging and graphics profiling. And at the lower level, we have some libraries which will allow you for GPU performance collection. So next slide, please. Just a different view of it. All the tools support all the application frameworks and the libraries which are available and work along with CUDA. So you have CUDA, OpenGL, Vulkan, Direct3D. These are the graphics APIs. As I mentioned, optics is for ray tracing. And the various frameworks, OpenCV, VisionWorks, the CUDNN, and so on. So all these tools work across these. I mentioned about these IDs. We have integration for these IDs, and the standalone tools are available for Windows, Linux, and Mac OS. We also have this SDK manager, which allows you to set up the development environment on the host and the target on some NVIDIA platforms, primarily Drive and Jetson. In terms of the target OSs, we support Windows, Linux on different CPU architectures, as well as x86 and QNX on the Tegra platforms for ARM AH64. And the GPUs are supported across all class of GPUs, right from anything which is CUDA capable, GeForce, Tesla, DGX, and the Tegra platforms. Next slide, please. So just a quick, when you're using the NSIGHT tools, this is kind of an overview of the workflow. You would typically start with the NSIGHT systems tool, which I mentioned which provides application-wide view. We'll see some screenshots here, and it will help you to narrow down which parts of the application are the bottleneck. And after that initial analysis, and you try to maximize the overlap between the CPU and the GPU, and you identify that a specific CUDA kernel is a bottleneck, then you would go to NSIGHT compute, which we will look at these tools in some more detail. Otherwise, if you're also using some graphics APIs and you identify that the graphics shader is a bottleneck, you would go to NSIGHT Graphics. And of course, after you do that optimization, you will come back and see, look at how the application level performance has improved. So you will again come back to NSIGHT Systems. So that's kind of the suggested flow. And as you know, optimization is an iterative step, and you will try and target one bottleneck at a time and go for higher performance. Next slide, please. Yeah, so now we'll have a quick overview of the debuggers available for CUDA. Next slide. So In terms of debuggers, we have, just like was mentioned for the HPE, we have an extension to GDB, which, so if you're familiar with GDB, it extends the syntax for GPU side kernel debugging. So you could do an integrated CPU plus GPU debugging. All the standard features of a debugger would be supported: single stepping, breakpoints, and viewing the state of your each of the variables for each of the threads. So here is a screenshot of the CUDA GDB integrated into the Visual Studio Code edition, where it shows you the source code and the breakpoint at which you are, and it shows you the state. It also has a console where you can type in commands, so that makes it really convenient. It shows you your breakpoints, and this is the state of your variables here. And as I mentioned, you also have integration into Visual Studio or Visual Studio Code, where you could, this is an example of doing that. And you could also remotely debug on Linux or Windows targets from. Okay, next slide, please. Yeah, just some more detail on the CUDA GDB. As I mentioned, it's a unified debugger. It shows you both, you could be doing single stepping or viewing the state at the GPU assembly level, which we refer to as SAS, or at the high level CUDA C level. It is built on GDB and uses, so it's basically an extension to that syntax. So it shows you here some CUDA specific extension where it is showing you all the threads at the all the breakpoints, and it will tell you for each of the thread, the block index, the thread index, which SM it is running on, what is the warp ID, lane ID, and so on, what is the source line. Similarly, you can see it for a specific breakpoint or a specific lane. Next slide, please. Now we'll briefly look at the correctness checker tools. Next slide. So Compute Sanitizer is a tool which is actually a collection of tools. If some of you have used CUDA memcheck earlier, this is the newer version of that. It basically has supports all the functionality plus several new enhancements. So the main subtools as part of this is memcheck, which is for identifying any memory access errors or memory leaks, racecheck for detecting shared memory access hazards, init check for identifying any uninitialized device memory accesses, sync check for any thread synchronization related hazards. So these are all command line tools. Here you on the right, we see a screenshot which is running the leak check and this is the application which is showing that. It shows you that you have an invalid global write of this size at this specific PC address in this source code in this particular kernel with details of the call stack. Just a quick overview of some new features added to be able to, because memory checking adds overhead. If you want to filter and restrict the checking to be done on certain kernels, you can select the count of kernels and you could skip some kernels. So these are new options. And similarly now for memory leak check, we have removed a limitation. You don't need to have the CUDA device reset call made. And for memory check errors, now we also give information for the nearest allocation, so that will make it easier to identify the exact allocation which was resulting in the error. Next slide, please. Now we'll have a quick overview of the NSIGHT systems, the platform level tool. Next slide. Yeah, so as I mentioned, it is the tool you would start with for a system-wide analysis. It will show you an integrated timeline across multiple processes, threads, both on the CPU side as well as all the GPU switch utilization and so on. We'll see some more details there. So it basically collects large number of events across all the libraries and underlying processes which are running, and it presents them in a hierarchical fashion, and it allows you to analyze the gaps where the CPU or the GPU may be underutilized. And it helps you to basically balance your workload and improve your overall application performance. So you could see how, yeah, we'll see more details there. It's available as a command line tool or as a standalone UI tool, or also integrated in to some IDEs. And it's supported across on Linux and Windows across these CPU architectures. And on Mac OS, you can load the target and see the results, but you cannot really do data collection. And it's supported on all GPUs with Pascal onwards, GPU architectures. For more information, you can look at this website. Here are some screenshots shown here. We'll look into some details. These are some different views of NSIGHT system. Next slide, please. So this is the main view which is presented, which is the timeline. And you can see there's a lot of data, but it makes it easy to try and analyze. We'll just see some key fashions here. Here you have all the rows with information about the rows, and you can either minimize and collapse them and look at those of interest. So for example, on the CPU side, you can see all the threads running and which cores are they running on, where they migrating across threads, because that could be potentially one reason for some performance issue. Similarly, you see this thread execution state, and you can identify regions where the thread was blocked or idling. As I mentioned, you can see the state for all the processes and threads. The specific things of interest here is now on the GPU side. You can see all the, so whatever APIs, like here we are seeing CUDA APIs, the CUDNN libraries, and the cuBLAS library. So this particular application is using those across all those processes. And then when you go down at the GPU level for each GPU, it will show you the memory transactions and the kernel execution. So the kernels here are ordered based on the utilization. There can maybe a lot more kernels, but they are not of importance. Of course, the focus would be to analyze kernels which are utilizing significant portion of the GPU. And so we will see the kernel and memory transfers. And below here, if you have multiple nodes on the GPU, you can similarly see the details for all those GPUs. Next slide, please. Yeah, this is just getting into details of, you can select a specific region and zoom into it. And if you click on, say, an API, it will highlight all the corresponding events across the different rows related to this. So for example, this CUDA graph instantiate, what are the launches made, what are the kernels which get triggered. So that correlation is kind of a unique feature that can be done across all these rows. Next slide, please. Yeah, we'll just have a quick overview of some of the new features added in NSIGHT systems. Next slide. Yeah, one useful feature, I think, which will be important on clusters, we talked about running on multiple nodes, and you could tile together multiple reports. So here we see two reports which are loaded together, and it would allow you to analyze they are correlated on the same timeline. So for example, if you are loading on, say, one node and the second node, now you could actually load them together and do the analysis and see any differences which may be there across those nodes. So similarly, you can also tile horizontally. If you have snapshots collected for different time intervals, you could see them together in an integrated timeline. Next slide, please. Yeah, one interesting feature is since you have so much of data, we have added rules to analyze. So these are examples of some rules here. You want to analyze CUDA asynchronous memory transfers, or whether the GPU is starving, and so on. So when you select that, here I've shown an example where you have asynchronous memory transfers happening, but in this case, they are actually running in a synchronous fashion because you are using paged memory. So it highlights that, it points to that, and it also shows the corresponding highlight on the timeline, and it suggests that if possible, you could try and use pinned memory instead, which will allow them to be actually asynchronously run. So similarly, these are the initial rules. Of course, in the future, we would be adding more such rules, which will make it more easy to do analysis of large data across the application execution. Next slide, please. Now for the communication library, similarly, you for the underlying MPI, if you are using the UCX interface, which if it is layered on top of UCX, you will actually see the underlying UCX APIs which are launched asynchronously. This will help you in actually identifying whether there are any bottlenecks related to MPI communication or the underlying usage of the network interfaces. Next slide, please. Similarly, for the InfiniBand adapters, there is an enhancement which shows you the various metrics for the transfers which are happening over the network adapters. For example, the sent, received, and this will help you in identifying any congestion points. And of course, the key thing is you will be able to correlate this to the actual application state, which is also going to be seen in the same integrated timeline. So you can know that during this phase of your application, this pattern is possibly, and you can go about, so you don't need to go to another tool for the network analysis. So we are trying to integrate all aspects of it into the same tool. Next slide, please. Similarly, if you are using a direct storage device, of course, accesses to that, and if you're using the CU file library, then you could see the accesses happening, the APIs and the interfaces over the PCIe happening to those accesses for that local or network file storage. So that will basically help you, again, in a similar fashion to analyze if that is a bottleneck related to your network storage usage. Next slide, please. NVTX is the NVIDIA Tools extension. It allows you to annotate your application. You can add these APIs. It's a very useful feature where you can actually demarcate and identify different phases of your application and see it along with in the timeline. Now, one new feature which is added, that you could actually classify and add named categories. So that way, all events related to those categories can be seen together. So it makes it easy for the analysis. Next slide, please. Yes, so now we'll switch to NSIGHT Compute, which is the kernel profiling tool. Next slide. As I mentioned, if you identify that, okay, this specific CUDA kernel is what you need to identify, need to analyze, and then you would switch to NSIGHT Compute. It supports both interactive as well as non-interactive modes. You could be stepping through the CUDA APIs and identifying some errors related to API. So that way it allows supports API debugging. But the key functionality is, of course, the kernel profiling, where it will collect detailed metrics. And just like NSIGHT systems, we also have built-in rule systems which will help you with some guided analysis, because you have tons of metrics which are collected, and it will kind of identify what are the ones which you need to look at and what order you need to look through those. And the good part is all of these are presented in different logical sections. For example, the memory, we'll see some of those, and all of those are described in a textual file which you can customize and for your needs. Again, it's available as a command line tool, as a standalone UI tool, or also integrated into IDEs. And you could also do remote profiling from, say, a Windows host, say, to a different target cluster machine you may be having, which is a typical use case. And it's supported across all Linux and Windows, and the Mac OS is, of course, just to analyze the report generated, not to actual profile across the different CPU architectures. It is supported on all GPU architectures, Volta onwards. And for more details, you could look at this website. Next slide, please. Yeah, so this is the view which will, so the different data is presented in different pages. Here we are seeing the details page, and at the top it shows you a summary of the utilization. So what percentage of your SM, the compute unit, is utilized. So this kernel is, of course, just utilizing 22% of the memory, the compute, and 28% of the memory throughput. This is the duration for the kernel, and some high-level metrics are shown there. And as I said, as part of the guided analysis, there's a rule which gets triggered, and it says that you are exhibiting low compute throughput and memory throughput. Please refer to these sections, the scheduler statistics or the warp state statistics sections, and you can click on those and actually go to that section directly. In addition to these metrics, summary metrics, it shows you the same thing as a chart. The utilization and the detailed metrics are then shown in the tables below. So it's kind of a top-down view, and with the rules, it helps you to guide through these different sections. Next slide, please. Now this is showing one of the memory workload analysis section, where it shows you the different levels of memories, the device memory, the L2 cache, L1 cache, and the transfer sizes between those memories when your kernel is executing. You could also see by changing this option to see the bandwidth utilized for those transfers. And there is this heat map. So these arrows are color coded, these based on how high the utilization is. So you can see that there are a lot of reads happening from the device memory into L2. And the detailed metrics of which are used here are actually shown in the table below. And you could, and when you hover your mouse over each of those, it will give you details and information about the metric and more information on how to interpret those. Next slide, please. Yeah, one of the powerful features is it will help you to drill down and identify the bottlenecks at the level of your source. So this is the source view. It shows you on the right-hand side the GPU assembly, the SAS, and on the left-hand side, in this case, it's the CUDA C code. And it shows you for this instruction the corresponding GPU assembly instructions which are highlighted. And the vertical columns here, the metrics. And for example, it shows here that this instruction has stalls due to long scoreboard. And then you can go back and try and see what could be the reason for those stalls. So basically, through your rules, you would drill down to a specific instruction, and then there would be guidance on how you could remove that bottleneck. So you have this heat map shown on the right here, both on the high level and the source. This will help you to identify the instructions which are really having the bottleneck issues which you need to analyze. So next slide, please. Yeah, here again, we'll look at some new features in the recent version of NSIGHT Compute. Next slide, please. So this is again a part of the source view. You're seeing the GPU assembly, and if you want to see the register dependencies earlier, for example, if an instruction is stalled waiting for data to be loaded onto, say, from global memory into one of the registers. Now it's very easy to analyze that by looking at the dependencies. The read and the write points to that registers are highlighted and shown. So it can help in identifying those dependency chains. And similarly, we also show the live register counts. So you can identify, because the number of registers you use will basically determine how many blocks can concurrently run. And based on that analysis, you can identify that, okay, you could possibly change your compiler options to reduce the register usage or modify your code, and so that you can launch more blocks and get better utilization of the GPU. Next slide, please. So the source view was, there were requests where people wanted to use it independent of the profiler. So you can now directly load and view your assembly and source just by opening the generated CU bin file generated by the NVCC compiler. So that's just a convenience feature, and it was added based on the requests. Next slide, please. Similarly, the occupancy calculator, which helps you analyze the occupancy and what are the constraints due to which the occupancy is limited, was distributed or is currently still distributed as an Excel spreadsheet. But to make it more convenient to use, it's now integrated into NSIGHT Compute. And the good part is you could either launch it standalone, or from a profiled kernel, you could launch the occupancy, and it will preload the information for the parameters for the kernel, and below it shows you what are the limiting factors. So you could, for example, if registers is a limiting factor, you can play around and say, if I reduce my registers per thread from 16 to 8, will I be able to remove the limitation due to that? What will be my new occupancy which will be achieved? So those kinds of analysis you can do using this tool now within NSIGHT Compute. Next slide, please. So Roofline is an analysis tool which is used. It's been popular for CPUs, and we also added it more recently for GPUs. So this is an enhancement to that. So just briefly talking about it, on the y-axis, it shows the performance in floating point operations per second. And on the x-axis, it shows an arithmetic intensity, which is the ratio of floating point operations to the memory transfers. So this line here is basically the memory barrier, and this is the floating point peak for that particular GPU. So earlier we only showed it for the DRAM. Now in the hierarchical roofline, we could also show it for the other memory hierarchies, the L1 and the L2 cache. So you can see it for multiple levels of the hierarchy. So that's something you can enable and collect. And similarly, we have it for tensor. There's a separate section for tensor roofline. Next slide, please. Yeah, so I'm at the end. You can look at, of course, all these tools are available and available for free download as part of the CUDA toolkit. So this is the link you can go to. And we have public forums where you can post questions and get replies either from NVIDIA engineers or other CUDA developers. And you can get a lot more information across various tools and additional training material and documentation at this link. So thank you. I'll be happy to answer any questions you may have.
Thank you, Sanjiv. I'd like to add a couple of points while we're waiting for a question to come in. So the first thing that so as a person that has been working closely with developer, I'd like to give a rule of thumb type of suggestion about how to use the tool. And Sanjiv already highlights what's the workflow that we advise. So first and foremost, if you have an application that you want to port or optimize on GPU, always start with NSIGHT system. So they give you a full overview about what's going on CPU, on GPU, and how the two correlate. And then obviously, when you get a good coverage of GPU acceleration, then you can drill down with the NSIGHT Compute to kernels, and then understanding exactly what's going on at the hardware level, and how much you want to actually understand about what's going on at the hardware level based on the programming model you choose. But even when you drill down to the NSIGHT Compute, I think there are a few things that is worth always keeping in mind. And the one that is kind of obvious is that to achieve what we call the speed of light with the GPU, you need to have enough parallelism. So there's not much you can do if there's not enough paralysis exposed in your application. So that is one thing to look at. And obviously the tool helps to understand that part. Another thing to look at, for example, is this is more in the broader picture, is always consider AMDAL essentially. So if you have an application that is fairly flat in terms of profile, that has multiple routines, not each one of them consuming, let's say, a big chunk of the wall time, focusing on super optimized one routine that consume only 10% of the wall time will not lead you to 10x speed up. This is kind of basic, but it kind of obvious. So try to tackle as much as possible, as high level as possible. And as soon as you start to use the tool and move code on the GPU, what you also will figure it out pretty soon is that what was the bottleneck before disappear when you move to GPU, and then new one happened. So this is an iterative cycle. You start with inside system, do some work, profile, repeat again, etc., etc. So these tools are part of the full workflow that you do as a developer. Sanjay presented very well about how, because this is the typical way to interact with the tool, that is the graphical interface. However, most of you guys would probably want to use this tool on an HPC system remotely. So it's all documented. You can create a report through a command line so through a command line statement in your shell, in your job script, generate a file, copy this file on your local machine, and open with the GUI locally. So there's no lag with the SSH connection. You don't need to fire up a VNC. I don't know if it's allowed, a VNC connection or anything weird. So you can work asynchronously with the tool by running the job, running the tool, running the profiler on the system, move the report on the local system, and do all the analysis you want. Last but not least, this is another comments that comes from me talking with a lot of developers and listen to some of the, let's say, feedback that they have. And often what people tell me is that, oh, this is amazing. This is so much stuff, Filippo, but this is a lot to digest. I mean, how can we actually handle all of this? So obviously we document a lot of the material that you saw, but the reality is that a lot of the ability to understand where the bottlenecks are comes with the experience of actually doing the work. And the tool is just a way to, the tool provides some suggestion, obviously, but then every application is different. So please consult the user guide when you want to learn the tool, because there's way more than we can cover in 30 minutes or even an hour. But ultimately, the more you use it, the more you get to understanding about how things, correlate with your specific application, and then helps you on the task of actually porting and be productive in the way you do essentially GPU coding. So there is any other question for this session? It's a lot to digest, I know.